Legacy BIOS and UEFI BIOS. What are they? What are the differences? Well, hold on tight, we're going to get into that right now. So I guess the first thing to understand is, what do they stand for? Well, a legacy BIOS, or BIOS, stands for Basic Input-Output System, and UEFI stands for Unified Extensible Firmware Interface. Okay, great, but what does it mean? What do they do?
So what is it?
Well, they're both firmware, which is just a bit of software that allows us to manage the hardware of a system outside of the operating system. Hardware is just the tangible stuff, such as CPU, memory, graphics cards, storage disks, you name it. It's all hardware. There you go. Here's some hardware. Tangible. I can feel that. And that's it. So what do we need a BIOS for? Well, we might want to enable things, disable things, adjust the way something works, overclock a CPU, overclock memory, things like that. There's a lot you can do within the BIOS. The BIOS sits on a non-volatile memory chip, which is just a computer chip, which is attached to the motherboard, like this, and executed when the machine is powered on. So what's a non-volatile memory chip, you might be asking? Fair question. Well, it's just a small chip that's read-only, and it retains its state when its machine is powered off. You might also see this referred to as NVRAM, and that just stands for non-volatile random access memory. It's the same thing. So as I say, it retains its state, which essentially means when the machine is powered off, all the settings and any changes you've made to the BIOS will be retained when you next power the machine off, even if you unplug the power cable. I should add a little caveat there though, that on the motherboard, this is a motherboard, there is a small battery, looks a bit like this. And that battery helps the BIOS retain its settings. So if you were to remove that battery and the power cable, after a few seconds, the BIOS would revert back to its default settings, though the BIOS would still exist. That will never disappear off that chip just by unplugging power. So how do we make changes to the BIOS? Well, we get into the BIOS configuration utility by pressing F2, F9, F10 or delete, or maybe another key depending on the manufacturer, when we first power the machine on. You might see something like this when you turn your PC on, or your server, or any other device that's got a BIOS. So a BIOS just provides some important but rudimentary control over the hardware of a system. It can't do things like render graphics or anything intensive like that. The legacy BIOS, which was used up until around 2007-2008 when the UEFI standard was, well, standardized and released, relies on something called a master boot record, MBR for short. The UEFI system does not rely on the master boot record. There is something called a protective master boot record, which is there for backwards compatibility, but that's not for this video and not really relevant to what we're talking about here. The MBR exists within the first 512 bytes of a storage device, and it contains a bootloader, a partition table, a boot and disk signature, and a disk timestamp. Disks that have an MBR are usually partitioned using the Disk Operating System Partition Schema, also known as DOS. How disks work and how they're laid out isn't really for this video, but I'm going to get into them just a little bit anyway, so hang on tight a second and we'll just quickly go through it. The first part of the master boot record contains the bootloader, and that's 440 bytes in size. If there is a disk timestamp, that will grow to 446 bytes. This is followed by a disk signature, which is essentially just a unique identifier for the hard disk itself. The partition table comes next, weighing in at 16 bytes per partition entry. It just describes how the disk is partitioned up, basically how it's been separated up. The boot signature comes last and is only 2 bytes in size. And without going into the details of how a boot signature works, basically what happens is, if a BIOS detects a boot signature, then it's automatically pointed back to the start of the disk where the bootloader starts so it can start the boot process. Disks that use the DOS partition schema can be no more than 2.2 terabytes in size. If you have a disk that's larger than that, only 2.2 terabytes would be detected. And they can only support up to 4 primary partitions. So you can't have more than that unless you use something called logical partitioning, which again, I'm not going to get into in this video because that's about disks. Disks being used on UEFI-based systems use something called GPT instead of DOS. GPT stands for GUID Partition Table. GUID just stands for Globally Unique Identifier. Disks using GPT can support up to 9.4 zettabyte disk sizes. That's 9,400,000,000 terabytes. That's a lot of disk space. In fact, there is no disk of that size right now. So you can see there's room for growth. They can also support up to 128 partitions on a disk. So there's a lot more space and partitioning available there. There's a lot of mathematics that goes into why the max partitions are what they are in both DOS and GPT. It's to do with block sizes and more information, but I'm not going to go into that right now because this video would go on much longer than it should do. This is about the BIOS, not disks. So I'll leave some information down below and you can go and check that out at your own leisure. I won't go into each section of the GPT disk here either because doing so would take a long time. I'll put a little image up here now and you can have a look at that. So you can see now how it's laid out in comparison to how the master boot record style disk is laid out. And there's a little bit more going on here too. So in that first part there, where the partition header is, there's actually multiple sections. So again, I'll leave some information down below and you can have a little look at that yourself. LBA in the image above stands for logical block addressing. Logical block addressing is basically there to indicate the location of the blocks where data is stored. Again, this isn't about disks, this is about the BIOS, so I won't be going into that in detail. Each logical block is 512 bytes by default. Okay, so I got a little bit carried away there with disks. I'm not going to carry on any further because I will just ramble on about it, and I've already rambled a little bit anyway. So let's go back to the BIOS and talk about what actually happens when you press the power button on your machine. As I mentioned previously, the legacy BIOS relies on the master boot record, and the master boot record contains information to help the BIOS boot. So how does the BIOS know which disk it's on? Well, previously I mentioned that disk signature. It looks for that on a disk, and if it finds it, it presumes this is the MBR, goes to the start of the bootloader, and starts the boot process. So how does it know which disk to look at? There's something in the BIOS configuration utility called the standard boot order, and this defines which devices are used to boot. So you might have a CD-ROM, a floppy disk, in a legacy BIOS situation anyway, a USB stick, and some hard drives. If you have more than one hard drive, then you'll need to define what order those hard drives are read in. However, it could be the last hard drive, and if that's the one that's read and has the master boot record on, it will still boot. It doesn't really matter. So what actually happens when you press the power button on the machine? Well, the first thing that happens, very quickly, generally, is something called the power on self-test. This is responsible for identifying simple hardware failures on the machine. Say your RAM isn't plugged in properly. Your memory.
Memory is RAM.
Or the CPU has an error, or a fan has an error, isn't spinning up properly, or something like that. Generally speaking, this will be detected by the post process. The next step is that it enables basic hardware components such as video, keyboard, and storage devices. Once that's been completed, the first stage of the bootloader is enabled. And then in the fourth and final step, the first stage of the bootloader loads the second stage of the bootloader, which generally exists within a partition on the disk, and that is responsible for presenting boot options and loading the kernel of an operating system. I'll get into kernels in a later video when we talk about operating system and kernels and things like that later, but right now I'll just give you a brief overview of what they are. So firstly, they're not these. These are different kinds of kernels. The kernel of an operating system is responsible for process and memory management, networking, file systems, and much, much more. So that gets booted first, which is then responsible for loading up the operating system. So now let's get into UEFI. UEFI doesn't rely on the master boot record, again, as I mentioned previously. UEFI instead relies on the definitions that are stored directly in the NVRAM. EFI applications are stored on an EFI system partition, also known as ESP, within an EFI directory. So it's kind of like a boot directory. The NVRAM has definitions which are then just indicators of the locations of those EFI applications. So each one would say, hey, this application lives here. Any compatible EFI applications can generally be booted automatically or loaded from a boot menu. They must exist within a conventional storage partition in a compatible file system. The compatible file systems are FAT12, FAT16 and FAT32 for block devices, USB sticks and storage devices to me and you, and for optical media, CD-ROMs, it must be ISO 9660. UEFI allows for much more sophisticated tools than that which is possible with a conventional BIOS. EFI applications can be things like operating system selectors, bootloaders, repair and recovery tools, and more. You may have noticed when you reboot Windows 10 into its repair mode, it seems to actually reboot into a new system. Well, essentially that's what's happening. That is another EFI application, which is separate technically from Windows 10 and 11 itself. So what happens when you press the power button on a UEFI-based system? The first two steps are exactly the same. The post process happens, and then the enabling of hardware. But the next two steps are where it differs. So in the third step, the UEFI system loads the definition stored in the NVRAM, which then executes the predefined EFI application, which is stored in the ESP system partition. Usually, that EFI application is a bootloader. I know, a mouthful, right? Basically, the third step, the UEFI system goes, hey, you, boot, to the EFI application. That's it. The definition just says, here it is, now go boot it. That's all. So that's what happens in the third step. The fourth step is that if that EFI application is a bootloader, it then loads the kernel, which in turn loads the operating system, which is a bit similar to the fourth step in the legacy BIOS. With both legacy and UEFI BIOS, if the post step does error, you'll usually get an error on screen. If you have one of these speakers attached, known as a CMOS speaker or BIOS speaker, then you will also get a series of beeps. Those beeps usually indicate what kind of error it is. And it'll be like beep, 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 beep. It won't, that's more like Morse code, but you get the idea. If there's no errors, then it'll just beep once and then off you go. Here are some examples of some of the errors you might see when booting a system. This one comes from a legacy BIOS. Now this is actually an HP server, and this HP server has something called hardware RAID installed within it. It's just a PCI card, which is a peripheral component interconnect card. We'll get into PCI and things like that much later. And this is responsible for managing redundancy of disks. So I have multiple disks in this system, and one of them has failed. It's this one just here. There you go, there's the disk. This disk died a while back, and I took it out, ordered a replacement, and I'm getting ready to install that soon. Thanks to RAID, I don't have to worry about data loss. RAID, by the way, just stands for Redundant Array of Independent Disks. I'm not going to get into RAID right now. All you need to know is that this disk right here is mirrored over to another one, which means that because this disk died and it's been removed, I don't have to worry about data loss because it also exists on another disk. We'll get into RAID in a later video about disks, but all you need to know for now is this one's gone. We don't care. It's fine. Goodbye disk. We throw that away, replace it with a new one, plug it in, and then that disk will be filled with the data again over time, thanks to the hardware RAID card. The point is, I got an error on screen, and that came up saying, hey, warning, this disk has failed. So this one right here comes from a UEFI-based system, and this is telling us that the CPU fan has failed. Now that actually is not true. What I did was remove the connection to the CPU fan pins and put it into a different one, just to make the error occur. Just to show you really what it looks like. Now, this prevents us booting up. It means that what will happen now is it will go into the BIOS configuration utility and will stop there. It's basically saying, look, I'm not going to boot the system because if I did, your PC would set on fire as far as I'm concerned. Now, it's not true. The CPU fan is still spinning because I've moved it to another fan header. But I just wanted to show you what an error might look like. There we go, we're done. It's okay, you can relax your brain now, try and take in what you've been told and go and make a cup of tea or coffee or something. So just to wrap up here, if you want to start playing with the BIOS configuration utility, then go into your motherboard manufacturer's manual and use that as you go through. If you don't know what you're doing anyway. If you do know what you're doing, then, well, I mean, why have you sat and watched this video? You shouldn't have been here. This was for the basics and the beginners. But, as I say, if you want to start playing with it, get your motherboard manufacturer's manual. That will have guides and information on how you can adjust things in your BIOS. Now, I wouldn't recommend changing things if you don't know what you're doing with them, but there's no harm in just having a look through. So in the next video, we're going to get into installing Ubuntu, and that's a Linux-based operating system. Linux is actually a kernel, not an operating system itself, and a lot of people will say, I'm installing Linux. Well, they are technically, but they're actually installing a Linux-based operating system. I just thought I'd get that little nugget of information out there. So we'll be doing that in a virtual machine, which is basically just a computer in a computer. And then we'll be moving on to more advanced things later down the line. So originally I was going to start by doing a set of Kubernetes tutorials. There you go. There's the Kubernetes logo right there. Little cushion my wife made for me. I love that. It's great. That's why it sits on my desk. And I sit and do Kubernetes all day, every day in my job. And that's why I thought I'd do a few tutorials on it. But I figured if people don't know how to use Linux and some of the underlying fundamentals of how Kubernetes works, then you're going to struggle understanding what's going on in that system. So I figured I'd go right back to the beginning, start with the BIOS, get Ubuntu installed, and then move on to more advanced stuff. So if you want to stick around for them, I'll see you in the next video. Ubuntu, Debian, CentOS, and many, many more. So I'm going to be going through that next. Disks using GPT can disks using GP VirtualBox, which again we'll get into later. My diffuser just fell down. So in the next video, well, that was a slog. My diffuser fell down. First video, great.